Hi guys, I'm back, and this time we're going to start to talk about the content in chapter 12, which is about groundwater. So I'm going to record, first of all, a lecture about the first few sections, and then we'll have a second video about wetlands, which is kind of the section at the end of the chapter. So let me share my screen here. Okay. Okay, so again, this is the first part of chapter 12, sections 12.1 through 12.4. Okay, so first of all, what is groundwater? Well, the name kind of implies that it's water that's in the ground, and that's true. But actually, not all water that's underground is considered groundwater. There's a certain portion of the water that's in the soil that we call soil moisture, and that's the water that's kind of bonded onto kind of the surface soil water particles. And as we go down, further down into the soil, we'll hit what's called the water table. And the water table is a place that kind of is the boundary between an unsaturated zone of soil where we have soil moisture, and then a zone below that where we have a saturated environment, which means that all the spaces between all the soil particles and all the fragments of rock that are down below the ground are filled in with water. So the diagram on the left kind of shows the surface zone with some water in the soil, the water table, and then the zone of groundwater below that. And often we refer to these areas where a bunch of groundwater is collected as an aquifer. So an aquifer is a porous layer of either rock, like fractured rock, or sediment, so like loose soil, that acts as essentially a reservoir for this water. So I think sometimes people imagine that these underground aquifers are like big open caverns, like caves that are filled up with water. And occasionally we do have kind of like limestone caves and stuff that can fill with water. But for the most part, this water is kind of just in between all these particles of sand, of clay, of silt, and then also of fractured rock. And the water kind of gets down into the ground by infiltrating when it rains through the soil over time. And so we refer to this process of filling up the aquifers as recharging the aquifers. And it's a long-term process. So if we have something that's taking water out of a groundwater aquifer, which usually is like a human-driven thing, like pumping from wells to access groundwater, then it's not something that we're going to be able to recharge or refill easily. It's something that will take a long time, hundreds of thousands of years to replenish these aquifers. And we can do certain things like allow water to sit over the surface on the ground where we know aquifers are sitting below. And that can be called like a recharge basin, which is something that I have a picture of here on the right. So that can help kind of accelerate the rate at which water would recharge. Or if you've ever driven through the Central Valley in the wintertime and seen a lot of like flooded rice fields, that kind of thing might also contribute to recharging groundwater. But generally, once we take water out of the ground, it's really hard to get it back in at the same quantity that we've had it in the past. So one of the things that we're going to talk about throughout this lecture is kind of the problem with unsustainable groundwater use. So that brings us to this idea of depletion of groundwater. And a lot of us depend on water that we pump out of the ground. About 50% of Americans depend on GW or groundwater as their water source. And this is particularly true in rural America, where we might not have kind of surface water, big like infrastructure. And even in places like Quincy, even if you're on the city water, you're actually getting groundwater. It's being pumped from wells. And a lot of times this water is being pumped from wells that unfortunately are kind of getting what's called overdrafted. That means the rate at which people are pumping water out of the ground is exceeding the rate at which the water is being recharged. And so kind of one of the most infamous places where this is happening is an area that's sometimes called the Ogallala aquifer, or sometimes referred to as the High Plains Aquifer, which is in kind of the central part of the country. This is kind of the area that was home to the Dust Bowl issue back in the 1930s, where a small drought combined with plowing up lots of native prairie land led to a huge kind of crash of the agricultural system there, and a lot of wind-blown erosion. Since then, people have put in extensive well systems to support agriculture in this area. So since there's not enough surface water and rainwater to support agriculture, they're pumping water out of the ground. However, they're doing this at an unsustainable rate. They're using a lot more water than is ever going back into the aquifer. And so what we're seeing is there's big declines. So this particular picture on this slide is showing from 1980 to 1995, so a little bit out of date, but shows you the kind of the trends that we're seeing here that are even more exaggerated today. And in some places we have, so this is inches drawdown, more than 40 inches of drawdown. Oh no, sorry, this is feet. That's what I thought, it was more extreme. So the red areas have seen more than 40 feet of loss of water underneath the ground over that 15-year period. So gives you an idea of how fast this water is being depleted. And then we're also seeing a lot of problems like this in California as well, particularly in the Central Valley, where we have lots of agricultural use, all kind of pumping water from wells at the same time. And groundwater, unlike surface water, is much less regulated. And so far, mostly people have the opportunity to essentially pump as much water as they can get without a lot of thought about how that might impact their neighbors or impact their future ability to access this water. So a lot of times people use the analogy of, like, you know, if you have 50 straws in a milkshake and everybody's just taking a sip of that milkshake, it's going to go down really fast compared to if you just have like 1 or 2 straws in the milkshake. And so this is kind of what we're seeing in a lot of these places, like over the Ogallala Reservoir, or like over the Sacramento or San Joaquin valleys in California. So there's a lot of different ways that we're trying to track and understand how groundwater depletion is taking place. One interesting way is through satellite data looking at gravity. And so gravity, as we've talked about in here before, is a force between objects that have mass. So the more mass there is, the more attraction there is, or more pull there is on other objects. And that is a force that can actually be sensed. And so we can tell how much pull certain areas of ground have on objects around them. And ground that's saturated with water is more dense, it has more mass than ground that's not saturated with water. And so it has actually a different gravitational pull on objects that can be picked up all the way from space, which is pretty impressive. So there's this one satellite that's called the GRACE satellite that has been flying around trying to get a sense of how much water is underground. And they've been doing this in places like California as well as other places. And we can see that the cumulative water storage under the ground has unfortunately been depleting over time. And so since 2011, 12 million acre feet have been lost per year in the Sacramento and San Joaquin River basins. An acre feet is a unit of water that's equivalent to an acre, like about the size of a football field, 1 foot deep. So if you filled up a football field 1 foot deep with water, that would be 1 acre foot. So we're losing 12 million per year. That's the rate that we're pumping in excess of the rate that we're recharging. So we're definitely drawing down this reservoir of water at a rapid rate. And we have a lot of concerns about what's going to happen in the next decade or the next 20 years when all of a sudden this reservoir is empty or near empty, and we've built up an infrastructure that's very dependent on this source of water. So California water use shown in MAF, million acre feet, shows different kinds of uses. agricultural uses, urban uses, and then environmental uses are basically just like the amount of water that we let flow in streams, for fisheries, for recreation, etc. And we can see that places like the San Joaquin River Basin and the Sacramento River Basin have pretty high gross agricultural use compared to like urban use and environmental use. So anyway, just to kind of get a scale of like how many acre feet we're talking about, 12 million acre feet is a lot of water that can have a measurable difference. Okay, here's another kind of look at this issue. So unsustainable groundwater pumping is depleting reserves in the Central Valley. So this is showing Sacramento, San Joaquin, and then Tulare Basin. So Tulare is like in the southern Central Valley area. And this is showing cumulative change in groundwater storage in millions of acre feet. And we can see that Sacramento and San Joaquin are actually a little bit more stable than the Tulare Basin, which is like kind of in the area of like Fresno, Bakersfield zone. And this is showing a much more extreme drawdown even than those other areas that I've already mentioned. So again, this is like a very well documented issue that we have a lot of concern about. So one other issue that it mentions in this chapter is the issue of subsidence. So as we're pumping groundwater out from the water or out from the ground, we are, first of all, just removing that water. So we have an inability to use that water necessarily in the future. And so we talked about why that might be a concern for these agricultural industries that are dependent on it, as well as just other rural community uses. However, another thing that we see is that as the water is drained from the ground, it actually causes subsidence of the ground. So the ground collapses down into the place where the water used to kind of be buoyantly pushing the soil particles apart. And this literally changes the surface of the ground. And so there's a famous photograph that you see in most groundwater discussions about California that I have shown here on the right. And this is showing the surface of where the ground level used to be in 1925 on this power pole, then 1955, then 1977, and then it's considerably lower than it was in 1977 today. So the actual surface of the ground is maybe not extremely important in most places, but it's an illustration of how much water has come out of the ground. And it could be a significant problem if you're in somewhere like the Delta region and you're experiencing subsidence that's causing you to actually drop below sea level, and then you're experiencing saltwater intrusion into your groundwater sources or into your agricultural fields and communities. That's creating some real problems for you. So again, kind of the lack of groundwater management is one of the things that's kind of led to this overuse problem. We don't have enough surface water to go around compared to what people are wanting to use. And so we've turned to the groundwater, and that's been kind of a stopgap measure, but it's not really a sustainable measure that we can expect to have adequate access to in the future if we're continuing to use it at the rate that we are. Another thing that can happen in an extreme subsidence situation is that we can have water underground between soil particles, or especially if it's like filling up some sort of limestone cave. And that water is actually more dense than the air. And so it actually provides a little bit of strength in the ground. And then sometimes when we pump water out of the ground too fast, if we have little areas like caverns and caves underground that have previously been filled up and kind of held together by the water, when the water disappears, the air inside the cave is not strong enough and the ground will collapse down into that underground cavern. And that's what is a sinkhole. So you may have seen these kinds of things in the news before. They're very dramatic. They almost kind of seem like National Enquiry, like maybe this isn't true, but in fact, this is a real phenomenon that happens, and it has to do with movement of groundwater under the ground and then leading to a lack of strength of the ground. So anyway, groundwater is a big issue. It's something that we hear a lot about in California. There's a lot of discussion about how we can implement regulation that will help us kind of use this resource more sustainably so that we can continue to have access to it. There are also concerns about groundwater quality. As we pull groundwater out of the ground, it's much more likely to be contaminated with different kinds of maybe even naturally occurring heavy metals that might be in geologic materials in the ground, or with like pesticides or nitrates or other things that have leached into the groundwater from the surface. And so it's important that we understand there's potential for contamination of groundwater as well. But it's a very important resource, and we hope that we'll continue to have access to it with wise management. Okay, that's a stopping point for my discussion of groundwater, and then we'll have another video about wetlands.